Okay, so welcome everybody, and it's my pleasure to virtually welcome Courtney Dressing. Courtney did her PhD at Harvard University about the prevalence position of small planets, after which she became Sagan Fellow and moved to the much hotter California on the West Coast, making collaboration with her European partners just slightly tricky. She moved on to becoming an assistant professor at the University of California in Berkeley since a couple of years now. Her main interests lie in finding exoplanets orbiting nearby stars and occurrence rates of these planets around a variety of different stars. Courtney, all yours.
Thank you so much for this invitation. I wish that I were there in person visiting all of you, but I had a lovely visit a few years back, and I hope to see you again in the future. I really enjoyed talking with the students before the talk, so thank you for that opportunity. Today, I'm going to tell you about some of the work that my students are doing, because it's been a challenging time for them to go see the world, so I want to advertise for them. We're going to be focusing on planets detected via two means: the transit method, which allows us to measure planet sizes, and the radial velocity method, which allows us to measure planet masses. For those who are not exoplanet experts, on the left here, what you're looking at is a movie showing our own sun, complete with sunspots, and this black dot, the planet Venus, crossing in front of the surface of the sun. Because the sun and Venus are both close to us, we're able to actually see Venus crossing the disk of the sun. And we could tell then that the planet exists and has a certain orbital period based on how long it takes between when Venus crosses in front of the sun. When we look at stars farther away, some of those stars are also blocked by transiting planets, but the stars are so distant that we're not able to actually see the disk of the star or the planet. Instead, we can infer that the planet exists by measuring how much light we see from the star and looking how much fainter the star is when the planet's in front of it. We can determine the planet's size relative to the host star size by looking at the fraction of the star's surface that's blocked and the orbital period based on the time between consecutive transit events. On the right, this cartoon here shows a hula hooping star with a planet on the hula hoop. So if you've hula hooped, you know that when you hula hoop, your hoops trace a small circle and the hoop traces a big circle. In this case, the planet is covering the big circle and the star is tracing the small circle. The planet and the star are both orbiting the joint center of mass, which is much closer to the center of the star than to the center of the planet. And that will cause the star to periodically move towards us and away from us. As Annalise knows extremely well, we can then measure the radial velocity of the star to infer the mass of the planet relative to the star. This works best when the planet is aligned and is also transiting, because then we get the maximum signal amplitude. But we can also use it for other orientations. And in that case, we'll just measure the component of the star's velocity parallel to our line of sight. So we'll be measuring the minimum mass of the planet in a generic circumstance rather than the true mass. For fun and for students who work in other fields, I've included two animations for what these effects look like. So the first animation will show us the transit effect. On the top here, we have a star with a planet. When I click play, the planet will start moving around the star. We start off in a face-on orientation where we wouldn't see any transits and we would be hard-pressed to measure the radial velocity. When we play, though, the system will switch orientation and move to edge on. So we'll see the planet cross in front of the disk of the star. We'll also keep track in the lower left here of how much light we see from the star versus time. When the planet is not blocking the star, we'll have a constant amount up here. But when the planet crosses in front of the star, the amount of light will decrease. So let's see what happens. We'll flip our orientation now. And we'll have the planet start to cross onto the disk of the star. So we have constant light, decrease in light, less light during the transit, and then we go up to the baseline level. This looks like a really big effect here, but we'll see soon that these effects are quite minuscule and therefore difficult to detect. For the radial velocity effect, this is our animation. We have, again, a star and a planet. This is rather exaggerated because it shows the star taking quite a big circle, when really the star is probably barely moving at all. We would not actually see a big change in the star's position on the sky. And then on the bottom is showing what we actually measure, which is the stellar spectrum, complete with absorption lines, which will move redward or blueward as the star is moving away from us and towards us again. So this one is a little bit less technical than the previous one. There's no graph involved, but you could imagine using a spectrograph, say HARPS North or maybe HARPS 3, to measure the radial velocity of the star and then infer the mass of the planet. You could also then look for additional planets in the system and perhaps even larger separation stellar binaries. Now that we've seen these animations, let's have a bit of a reality check and see how large these signals might be. So if we use the solar system as a metric, we could consider trying to find a planet like Jupiter orbiting a star like the sun. In that case, we would expect to see a decrease in brightness of 1% if Jupiter crossed in front of the sun. The challenge here is that Jupiter has a relatively long orbital period, many years, and it's unlikely to be in front of the sun at right the moment where we're looking. Plus, there's only a very narrow range of orientations where Jupiter's orbit would ever cross in front of the sun. So the idea that you would detect a planet like Jupiter via the transit method is a little bit far-fetched. You could do it, but it requires precise alignment and looking at exactly the right time. And the important thing to take away here is the size of the signal. It's 1%. I couldn't tell if the lights in my room got 1% fainter, but our instruments can definitely do that. A 1% signal is easy for us to detect these days. The radial velocity signal from a Jupiter-like planet orbiting a star like the sun would be 12.5 meters per second. This is also something that is well within the reach of current instrumentation. The challenge again is that the Jupiter has a long orbital period, so you need to look for a couple of years in order to see the signal turn over to know that you've actually found the period rather than just knowing that you have some long period massive object orbiting the star. Things are much more challenging if instead of Jupiter, you're trying to detect Earth. For Earth, you would have a transit depth of 0.0484%, or 84 parts per million. That's teeny. The NASA Kepler mission was designed specifically to figure out the frequency of planets like the Earth orbiting stars like the sun. And even after staring for many years, for 4 years, at the same set of stars, Kepler was just barely able to reach this sensitivity. So 84 parts per million, the transit depth for an Earth around a sun-like star, is something that we can do, but only with a dedicated survey and multiple years worth of observations from space with a facility that's extremely precise like Kepler. So this is hard. The next part is even harder. The radial velocity signal for an Earth-mass planet orbiting in a 1-year period around a sun-like star is only 9 centimeters per second. This is much better than what we can do currently. With the best instruments today, our typical routine precision is something like 1 meter per second. With the next generation facilities that are just starting to come online, when we look at really bright stars and we have everything lined up perfectly and it's a gorgeously clear night, maybe we could do something like 20 to 50 centimeters per second. But that's only under particular conditions, and it doesn't include the effects of stellar variability. So getting down to 9 centimeters per second is very, very hard. And this is something where the radial velocity field has been working hard to achieve this goal. And Annalise is one of the world's experts at trying to figure out how we can get closer and closer to this 9 centimeters per second. But for now, it's safe to say that using the radial velocity method to find Earth-mass planets orbiting sun-like stars is extremely difficult. But we want to be able to do that so we can study the densities and the compositional diversity of small planets. And personally, I'm very interested in knowing whether any of those planets might have life. And one of the first steps along the way is to figure out the bulk density of the planet. From the Kepler mission, by detecting the transits of planets orbiting hundreds of thousands of stars, oh, and then just for fun, when I give this talk in the US, I have to say that 12.5 meters per second is like driving speed and 9 centimeters per second is like slugs. But you all know that because you use a proper system of measurement in the UK. All right, so when we look at planet occurrence rates from Kepler, one of the things that stood out right away was that smaller planets are much more common than larger planets. This figure here is from a 2013 paper by Andrew Howard, where he's plotting the number of planets per star as a function of planet size. So we go from 1 Earth radius all the way up to 22.6 Earth radii. You might say that these numbers are a bit large, but we can imagine that these are inflated Jupiters that are so close to their stars that they've puffed up due to the high insulation flux. When you look at this chart, seeing that there are lots of Earth-sized planets is encouraging and exciting. But at the time, this population in the middle, all of these planets between 1.4 and 4 Earth radii, was a bit perplexing. These planets are larger than the terrestrial planets in our solar system, yet smaller than the ice giants. Uranus and Neptune are about 4 Earth radii. So looking at just the solar system, we don't have a good handle on what these objects are because nothing like them exists in the solar system. We can try to figure out what their compositions are by measuring both their mass and their radius and seeing how they compare to various models. So if we do that, we end up with a plot like this one from Carolyn Doran's 2018 paper. If we show the planet size versus planet mass and zoom in on the small planets, so we'll go from 1 to 3.5 Earth radii on the left, 1 to 10 Earth masses on the bottom, we'll see that we end up with kind of 2 clusters of planets. We have a bunch of planets clustered here. These planets appear to be small and relatively high mass for their size. And then we have planets over here. These planets are on the right side of the diagram, so they're massive, but they're also in the upper right, meaning that they're large for that mass. Earth and Venus are down here in blue. And if we look at these colored lines, they're showing different recipes for how to build planets. In red, we imagine a ball of pure iron. That's pretty unrealistic. We're not going to be able to just get pure iron without some other elements as well, but it's useful to have for comparison. In yellow, we have a model that's pure magnesium silicate. So you could think of that as kind of pure Earth mantle. Earth and Venus lie just below that line, showing that they also have iron-rich cores. So if we wanted to approximate an Earth-like composition, we would have a line that ran just below that yellow line. So maybe something like here. And we would see that it would run through this population of planets over here. In blue, we're showing planets that have a much higher fraction of water ice. These planets, the ones up here, lie above those blue lines, and therefore they cannot be explained by an Earth-like composition. They require a much higher fraction of lighter materials like water or hydrogen or helium. And Madhu's group has been working hard to figure out what the atmospheres of these planets are and see what angles those can give us on the compositions of these planets. Looking at this with broad brushstrokes, though, you could say that we've learned so far that planets that are smaller than about 1.4 Earth radii have Earth-like compositions, while larger planets require more volatiles. Leslie Rogers had a famous paper with the title that planets smaller than 1.5 Earth radii are not rocky, or larger than 1.5 Earth radii are not rocky, because these planets do seem to be so large for their masses. So it's tempting to think that we've got it all figured out. But it's very important to look at the y-axis here. These are the equilibrium temperatures of the planets. And as you look at those, you'll see that these planets are not good analogs for planets like the Earth. We haven't yet reached the place where we're able to measure the bulk densities of planets with Earth-like temperatures, which means we don't really know what the composition of a planet of a given size would be if that planet is at an Earth-like orbital distance. This diagram is strongly biased towards hot planets. So we're seeing not just how planets form, but how planets have been sculpted over time by the irradiation of their host stars. So if we really want to understand the compositional diversity of small planets in general, we need to expand our frontiers to try to fill in that diagram. We need more planets overall, for which we've measured mass and radius. And we also need to push out to longer orbital periods and lower insolation flux, so we can disentangle how planets form from how they've lost their atmospheres over time due to effects like photoevaporation and perhaps core-powered mass loss. This is an effort that's being done around the world using a variety of radio velocity spectrographs. But for today, I wanted to show you just a little bit of one of the planets we've been working on over in California. Graduate student Andy Mayo, who is finishing up his 3rd year of grad school and just starting his 4th year. Graduation was on Sunday, so I suppose I should say he's a 4th year. Recently led a paper on the planet Kepler 538b. This was a planet that he started working on in collaboration with his Fulbright Scholar Advisor, Lars Bukov, who is in Copenhagen, and graduate student, or now postdoc, Vinesh Rajpal. This planet is what I consider to be a long period planet. And for those that don't study planets, you're probably looking at this and laughing, because in our own solar system, all of the planets have orbital periods longer than 80 days. So a period of 81 days is long for transiting planets, but still a very short orbital period compared to solar system planets in general. What you see here are data from the NASA Kepler mission showing the brightness of the star Kepler 538 versus time. And we're zooming in on the transit events. And we've set it up so that we're seeing 5 hours before transit, transit right in the middle, and then 5 hours after. So you can see this beautiful transit curve. The Kepler data are in black, the bin data points are in blue, and the model is in red. Using the Kepler data, Andy measured a planet radius of about twice the radius of the Earth, 2.2 Earth radii. And then using a combination of data from HARPS North, which are shown in blue, and HIRES, which are shown in orange, Andy and his team were able to measure the mass of the planet as 10.6 Earth masses. And here you can see that the amplitude of the signal, if we look at the gray binned data points, is something like plus or minus 2 meters per second. So this is small, but still a long way off from that 9 centimeter signal that we would like to be able to detect. If we place Kepler 538b on the mass radius diagram, this is where it falls. So on the left here again, we have planet radius, on the bottom planet mass. Now we're using gray lines for compositional models, but it's the same story. The ones on the bottom are more iron, the ones on the top are more lightweight materials. Venus and Earth are here for reference, and our Venus and Earth-like model runs about here. And you can see this plot now has more different planets on it than the Dorn plot you saw before, and that's mostly because this is a later plot and it's using a more relaxed cut on what we consider to be a precise measurement of planet mass and radius. Here, the data points are colored based on the orbital period, and this color scaling really makes Kepler 538b stand out. Everything else appears to be red, but Kepler 538b is in dark blue because it has a much longer orbital period than most of the planets in this region of parameter space for which we measured both mass and radius. So this is one example of extending the mass radius diagram out to longer orbital periods. And as we continue to make more precise radial velocity spectrographs and build up the baseline of observations, we'll start to fill out this diagram a little bit more, so we can turn it into a 3-dimensional data cube and look at insolation flux as a third axis. As you stare at this, you might be wondering why there aren't more planets on this diagram. I'm sure you all have heard of the Kepler mission, and you probably know that Kepler found thousands of planets orbiting nearby stars. Kepler launched in 2009 and finished operation in 2013, so we've had about 10 years to measure the masses of Kepler planets. You might think that that would give us enough time to add hundreds, if not thousands of planets to the mass radius diagram. But while Kepler was wonderful for occurrence rates and for figuring out the frequency of planets at various sizes and orbital periods, Kepler was not an ideal survey for mass determination because, and it wasn't designed to be, the reason why Kepler is not a good data set for measuring the masses of thousands of planets is that the Kepler targets are faint compared to the precision that we could need, compared to the brightness of the star we need to achieve the requisite precision with radial velocity spectrographs. So here, I'm showing a histogram of the brightness of the stars observed by Kepler to have one or more transiting planets. This is in Kepler magnitude, which is similar to V-band magnitude. If I make a somewhat generous cut as to which targets are good targets for, in this case, the Keck spectrograph, what we'll see is that only a small fraction of them are bright enough to be good RV targets. And really, 12.5 Kepler magnitude is not an ideal target. In many of our discussions of which targets to observe with Keck HIRES or with HARPS North, we really want to be over in this region of the diagram. The brighter the star, the more photons we get, and the more precise our radial velocity measurement can be. So Kepler found thousands of planets, but only a subset of those were good targets for radial velocity. And then once you make the cut on brightness, you also need to make a cut on the stellar activity level. And it's been difficult to try to find a large sample of planets that are bright, quiet, and have orbital periods that are small enough that we can measure the radial velocity amplitude. Fortunately, though, there's a new mission in town. The NASA TESS mission launched in 2018 and has been surveying the sky to try to find planets around stars that are brighter and therefore better targets for radial velocity mass measurement. Here on the left, you see a view that TESS took of the southern sky in the first year of the mission, and on the right, the northern sky. We're now on the extended mission and looking back at the southern sky to fill in some of these gaps and find even more planets. The way that TESS works is that the telescope has 4 cameras. You can see them here, 1, 2, 3, 4, each of which point at a slightly different field of view. So at a single time, TESS is looking at a strip of the sky. In the first year, one of those cameras was always trained at the southern ecliptic pole, and the others marched their way up towards the equator. That would look at TESS would look at one strip of the sky for about 27 days, so 2 TESS orbits, and then move over to the next strip, and then the next strip, and then the next strip. That means that you're observing these stars out at the limb for about 27 days, so you're sensitive to planets with orbital periods of roughly a week. And then you're observing the stars closer to the ecliptic pole for nearly a full year. So you're actually able to sense planets with orbital periods of multiple months. In the northern sky, the pattern looks a little bit different because it turns out the moon and the earth are bright and can make it hard to look for transiting planets. But the idea is the same. With TESS, you're getting these full frame images, not once every couple months, really once every couple minutes of the sky. And you're measuring the brightness of these targets and therefore able to detect transiting planets. With Kepler, we looked at particular stars and downloaded postage stamps, so the pixels close to the stars every 30 minutes. With TESS, we get the whole field of view on that time scale, and then postage stamps on a much faster time scale of a couple minutes. So TESS has much more sensitivity to planets orbiting a wide number of stars because we're getting more data and we have full frame images. At the same time, TESS is also a good mission for different types of astrophysics, like supernovae pre-explosion light curves, because you happen to get that data for free while you're looking for planets. With both TESS and Kepler, there is a challenge that not everything that appears to be dimmer on a periodic timescale is actually caused by a transiting planet. So if we look at a transit light curve from TESS, and we see that the star normally has 1 brightness and then gets dimmer every, say, 5 days, one explanation might be that that star is orbited by a transiting planet, but there are other explanations as well that could also explain the light curve. We might have a case where our target star is actually orbited by a brown dwarf or a low mass star. We might have a case where there's a nearby stellar binary, either something that is actually physically associated or just happens to be a chance alignment along the field, along the line of sight. Or perhaps we have a case where we have 2 stars that have a grazing eclipse. If we look closely at the TESS photometry, we'll see that the shape of the event might look different. For the grazing case in particular, we'll probably see that rather than having a U shape where we go decrease in brightness as a U and then back up, we'll have more of a V-shaped profile. But for others of these events, we might not have the precision we need in order to tell the difference between a blended stellar binary and a transiting planet. We would like to do as much as we can with the TESS photometry because ground-based follow-up researches are limited. We want to use them wisely. So for part of his PhD thesis, grad student Stephen Jackalone, who's going to be starting his 5th year in the fall, has worked to build a set of tools to vet TESS planet candidates. His code, which is called Triceratops, takes as input TESS light curves and then fits a variety of models to determine which of these events are actual transiting planets and which of them are more likely to be astrophysical false positives. His paper was published earlier this year in the Astronomical Journal. And in the paper, we looked at 384 TESS objects of interest and were able to statistically validate 12 planet candidates. What statistical validation means is that we look at the photometry and we consider the likelihood that those events could be caused by anything other than a transiting planet. And we're able to then rule out the idea that they were caused by something else. So we say that it's much more likely for those events to be planets than for them not to be planets. In the paper, we have the 12 validated TOIs. We also identify 125 likely planets. Those don't meet our threshold for validation, but they are promising candidates that don't appear to be false positives. And we also find 52 objects that are more likely than not false positives associated with nearby stars rather than the target star. In the paper, if you plot the types of objects as a function of magnitude versus temperature or radius versus period, you can see that they do separate out a little bit. In both of these plots, the new validated planets are marked as yellow stars, the likely planets are in green, and the nearby false positives are black squares. If we focus on the plot on the left, one thing that really stood out to me when I talked about these figures with Stephen is that many of the very short period objects happen to be false positives. So if you find a TOI and it has an orbital period of 1 day or shorter, odds are it's probably not a real planet. But if you find something out with an orbital period of 10 days, where all of these green and yellow dots are, maybe it is more likely to be a real planet. Using Triceratops, we're able to prioritize our follow-up and concentrate on the systems that are more likely to be real. For an example of how Triceratops works, this figure here from Stephen's paper shows a light curve for a particular object, that's the blue data with error bars, and models for a bunch of different scenarios. I don't expect you to read the labels for what each of these scenarios are, but it is a fun exercise to look at those models and the data and try to find the model that best fits the data. In this case, if you've been trying to do that while the slide has been up, you probably identified the top model as the best fit for the system. And in this case, that's correct. This is a known planet. This is actually WASP 166b. And in this case, we find that the best model is the TP model, the transiting planet model. For another example, here's a different set. And I'll give you a minute to try to find the best example for this one. The transiting planet model is still in the upper left. And you can see right away that that's a bad fit to the data. The model was much shorter in duration than the actual transit-like event. The best one is actually in the lower right. And this is a nearby eclipsing binary, NEB, at 2 times the orbital period of the transit event. This one has a false positive probability of over 99%. If you're interested in learning more about Triceratops, Stephen's paper is online, and you can also download the code from GitHub and use it yourself. If you want to use Triceratops to validate the system and you're having challenges getting the code up and running, or you just don't have time to do that, please send us an email. Stephen has helped validate planets for many papers, and he would be happy to validate TOIs for you as well. And now I'm going to transition to the next phase of the talk, which is the TESS survey. We mentioned at the beginning that Kepler found thousands of planets, and those were fantastic for statistics and occurrence rates, but not the best for measuring planet masses. TESS is a different story. TESS has been finding thousands of potential planets, and these planets orbit stars that are perfect for radial velocity follow-up. But that doesn't mean that we can just go look at all of them. We still need to prioritize which targets to follow up because we have a limited amount of radial velocity resources. For the past couple of years, I've been participating in the TESS survey, which is a combination of various University of California campuses, University of Hawaii, University of Kansas, Caltech, and Keck Observatory to use high-res on the Keck 1 telescope to measure the masses of a large sample of TOIs. We've selected our sample carefully so that we can build a statistical ensemble and address some big picture questions, in addition to understanding the properties of individual TESS objects of interest. With TKS, we have 4 science themes. The first of those themes is bulk planet compositions. We want to fill out the mass radius diagram to really understand why planets of certain masses end up with different sized envelopes and cores. Next, we want to understand the architectures of planetary systems. We want to know where all of the various planets are and understand correlations between the presence of inner planets and the presence of outer planets. Area 3 is atmospheres. We're all thinking about James Webb and Ariel, and we would like to know which planets have certain masses so we can prioritize their follow-up observations with James Webb. And then finally, the final branch of the TKS survey is to look at planets orbiting evolved stars to see what happens to planets as systems age. As we pursue these 4 science themes, in parallel, we're considering 2 technical goals. We're getting a large ensemble of stellar spectra, and we're using those spectra from which we measure radial velocities to also refine stellar parameters to get temperatures and metallicities and surface gravities. And then in parallel, we're looking at astrophysical Doppler noise by looking at the ensemble of our measurements and comparing the TESS photometry to the high-res data to try to be better at removing stellar noise from spectra when modeling radial velocities to determine planet masses. In order to select a sample of targets to address all of these goals, we put our heads together and came up with a set of prioritization metrics in order to identify what the best targets are for each of those scientific aims. This effort was led by Ashley Chontos, who is a graduate student at the University of Hawaii. And in this figure from her almost submitted paper, she's showing the overlap between the various science themes. Each of these big circles is one of those 4 science goals I showed you earlier. So in pink here, we have the bulk compositions goal. In dark blue, exoplanet atmospheres. In light blue, architectures and system dynamics. And then in orange, the evolved stars. We don't have overlap between the evolved stars and the system architectures categories, but we have overlap everywhere else. So by having targets that satisfy multiple science goals, we're able to try to get more science out of a given number of high-res observations. Overall, we're looking at 85 stars hosting over 100 planets. And we're working in collaboration with the larger TESS follow-up effort. So for some of our systems, we're contributing RVs to papers led by other teams. And for other systems, we've invited other teams to contribute their RVs to our papers in exchange for co-authorship. So this is a joint effort both within the TKS consortium and within the broader community. Looking at theme 1 for bulk planet compositions, on the right here, you can see the radius and period distribution of our targets. So different colors here indicate those science goals I showed you earlier. So if it has multiple colors, that means the target was selected for multiple science goals. So this one here has both blue and purple. So it was selected for science case 2, which is architectures, as well as science case 3, which is atmospheres. Within the bulk planet compositions case, we're hoping to address the following questions. Which small planets are rocky? How does the proximity to the star affect the atmosphere of the planet? Do we see that the planets that are close to stars have smaller atmospheres than planets that are farther away? What are the compositions of the hottest planets, those with orbital periods of less than a day? What are the properties of planets within the habitable zone, the distance from a star at which we might have liquid water on the planet's surface? And how do the properties of a planet depend on the properties of the star? As we dial up the metallicity of the star, do we also see that the planet gets more and more metal rich? In order to address that final point of star-planet property correlations, we wanted to select target stars that span the HR diagram. So here we look at stellar radius versus stellar effective temperature. And you can see that we're going all the way from M dwarfs up to F stars. We don't have any white dwarfs in the sample, but I was excited to talk to the students this morning about looking at planets orbiting white dwarfs and what we can learn by studying planets that are being eaten by their stars. We do have some evolved stars. We haven't gone all the way to the end stages of stellar evolution. We look at metallicity here. We go from -0.5 to 0.5, and we're also covering stellar masses of half a solar mass up to about 1.25 solar masses. So we tried to cover this diagram so we would be able to have a broad enough sample such that when we get all of the planet masses in the end, we're able to put things in context and really build a model that accounts for all of these different factors. On the architecture side, the questions that we're addressing are, what does the presence of an inner planet tell us about the presence of outer planets? Do other solar systems look like ours? Do they tend to have Jovian planets outside inner planets, or are they all jumbled together? What are the dynamical temperatures of small planets? By that we mean, do they have high mutual inclinations? Do they have highly eccentric orbits? Or do those systems tend to be flat, coplanar with low eccentricities? And then finally, what are the properties of multi-planet systems? For the planetary orbits, this figure from our proposal from a paper by McDougall et al. Shows the sample studied by TKS. So on the left here, we're looking at eccentricity. On the bottom, we're looking at semi-major axis. In turquoise, we're looking at the planets that were studied before the TKS survey that happen to be sub-Jovians. And in red, we're looking at the ones that are part of our survey. We also have some new proposed targets in the proposal that I just led that are marked by orange lines. So the idea here is that prior to TKS, many of the planets that have well-constrained eccentricities are Jupiter mass planets, and there aren't that many eccentricities measured for sub-Jovian planets. With TKS, we're expanding the sample of small planets that have measured eccentricities. On the right here, you see one of the examples from TKS already. This paper is going to be submitted probably in the next month. And in this paper, we've measured the eccentricity of this planet here, HIP 97166b. And then we also detected another planet in the system. One of the systems that I'm most excited about is the system 1246. This system is being led by my graduate student, Emma Tertelbaum. And in this system, we find not one, not two, not three, but 4 sub-Neptune planets, all discovered by TESS. The innermost planet has an orbital period of 4.3 days and is about 2.9 Earth radii. The next planet is a little bit further out, but about the same size. Planet 3 is 3.3 Earth radii, so a little bit of a size jump there, and has an orbital period of 18.7 days. The next planet is the same size as planet 3 and has a longer orbital period of 37.9 days. I'm sure some of you have already been comparing the orbital periods of these planets to each other. And if so, you've probably realized that these outer 2 planets are very close to the 2-to-1 resonance. So here, if we plot the period distribution of planets from Fabrici et al. 2014, and we overplot in blue the planet from the TOI 1246 system, you can see that the innermost planets lie here, kind of not really close to resonance. They're outside the 4-to-3 resonance. The middle planets, the 5.9 day and the 18.7 day, are over here. But the outermost planets, 18.65 and 37.9, lie just outside the 2-to-1 resonance, which indicates that they're probably dynamically interacting with each other, and they might have transit timing variations. When Emma fit the TESS photometry, she found that that is indeed the case. We do see transit timing variations for these outer 2 planets. We don't have enough TESS data to see the full super period of the TTVs, but fortunately the system will be reobserved in year 4 of the TESS mission, and hopefully that will help us close the loop on measuring the TTVs of these 2 planets. Excitingly, we have a data set from high-res of the masses of these planets. So we have tentative mass measurements for all 4. This slide is very preliminary, especially because we've also started collaborating with a team of scientists who have HARPS North data, and that has given us 25% more data than we had already. So don't place too much stock in these numbers. Those will change as we get the system measurements nailed down a little bit more. We're also getting more precise measurements now that Emma's doing a joint fit. But the key thing that we've seen so far is that if we take these 4 planets and we plot them down on the mass radius diagram, so we have planet radius versus mass, Venus, Earth, Uranus, and Neptune for reference, and then all of the other planets that are small that have measured masses and radii in blue, we can add the 1246 system in white. These inner 2 planets are right over here. The inner 2 planets, B and C, are the smallest. Those are these 2 right here. Planet D is this one here, and then planet E is over here. So the inner 3 planets all have masses that are consistent with each other. The outer planet appears to be much more massive. On this version, the error bars are large enough that you might wonder whether that's statistically significant. But as we've gotten more and more data, these error bars are shrinking. So we do see that this outer planet is much more massive than the inner 3. So this is a fascinating system because it provides an opportunity to study 4 planets all formed from the same disk at the same time, orbiting a star with the same metallicity, and compare their atmospheres. It would be wonderful to know whether we see compositional trends in the atmospheres of these planets that we can then use to reconstruct the story of when and where and how these planets formed. They probably did experience some migration, given that we have the outer 2 close to the 2-to-1 resonance. And it would be nice to have atmospheric data for the system to accompany the bulk densities. But for now, Emma, who is starting her 3rd year in the fall, and Lauren Weiss, who is a postdoc at Hawaii, are writing the paper that tells us the masses and the bulk densities of these planets. And hopefully in the future, perhaps scientists will have access to atmospheric data that tells us more about the system. But even the masses alone are quite interesting. Emma made this figure to put the system in context with other small systems. What you're looking at here are all of the 4-planet systems that we know about where 4 planets transit. They're ranked by the orbital period of the innermost planet. So at the top, we have K2266, which has an inner planet with an orbital period of less than a day. On the bottom, we have Kepler 79, where the inner planet has a period of 10 days. And then right in the middle, right here, we have TOI 1246. The planets here are shown according to the planet size. So the larger the dot, the bigger the planet. And they're colored by the planet mass. Right away, you probably saw that most of these dots are gray because we don't have masses for most of these planets. TOI 1246 stands out because it's one of only 8 4-planet systems where there are masses for all 4 planets. It's also brighter than 93% of the planets with masses for all 4. So it's an interesting system for future follow-up observations. If I back up a bit and talk about TKS more generally, our theme 3 was planetary atmospheres. So on this diagram here, you can see a plot of the stellar temperature versus insolation flux for targets that are interesting for TKS from the atmospheric perspective. So in stars here, we're showing the targets that we propose to observe in our latest Keck proposal. If we get time, that'll be for another year worth of Keck data. In circles, we have targets that we've already that other people have started to follow up already. And in the squares, those are the targets that we followed up with TKS during the initial stages of our survey. And you can see this is covering an interesting range of parameter space. And then on the right here, we're showing how easy it is to study the planet's atmosphere in the future. This is the transmission spectroscopy metric developed by Kenton et al. And yellow colors indicate more attractive targets for follow-up. So in our latest Keck proposal, you can see a lot of yellow stars because those would be fantastic targets for HST or perhaps James Webb. As we think towards the future of exoplanet characterization, I know that Madhu's group has been thinking a lot about how to study planetary atmospheres. And if we do that, one of the ways that we can do it with transiting planets is by looking at the star when the planet is not in front, and then looking at the star when the planet is in front, and seeing how the starlight shines through the planet's atmosphere. When this happens, the gases in the planet's atmosphere will leave a fingerprint on the starlight, telling us what the composition of the atmosphere might be. We'll be able to determine whether the planet's atmosphere has certain gases, whether the planet's atmosphere has clouds, and for other planets where we can actually get the full phase curve of the planet orbiting the star, or perhaps just a secondary eclipse observation as the planet goes behind the star, we can then figure out the pressure temperature profile of the planet's atmosphere and measure winds. We could look for our heat redistribution, see where the hottest point of the planet is compared to the part that's most illuminated. It'll be really interesting to get a data set for planets with James Webb to learn more and more about their atmospheres. I have to admit, I threw the atmospheres part into the talk partially because right now, with the Hubble Space Telescope, we're actually collecting data of a really interesting system. My team, which includes a wide variety of people from around the world, including, I think, Annalise, is looking at HIP 41378, which is a 5-planet system. This system was detected using photometry from TESS Kepler K2 that shows that there are 3 inner planets. In the initial photometry, those had well-defined periods. And then the outer planets in the system had single transit events, and their periods were not known. So in the discovery paper led by Andrew Vanderberg, they weren't sure what the periods of those planets would be. In a follow-up paper led by Juliet Becker, they were able to narrow down when the planets might transit based on looking at the available photometry and data gaps. And then finally, in a multi-year, multi-instrument, multinational radial velocity follow-up effort led by Alex Sozzetti, we were able to determine the real periods of the outer planets. And then once we knew those dates, we were able to figure out when the transits would be and apply for time with HST. So hopefully the next time I talk with all of you, I can tell you about the follow-up observations that we're taking right now to study the atmosphere of a really interesting Jovian planet that has the same temperature as the Earth. This planet has suspiciously low density, which might indicate that it's surrounded by a ring system. And that's one of the many things we're hoping to investigate with these HST observations. In the future, we're all counting down the days until the launch of James Webb. And with James Webb, we'll have a chance to expand our coverage of planetary atmospheres out to the mid-infrared. And hopefully with that larger data set and with higher precision observations at shorter wavelengths, we'll be able to finally understand what's happening in the atmospheres of those planets that seem to have annoyingly flat transmission spectra. We've seen that many of these planets look featureless. They probably have clouds. It would be wonderful to get more coverage to see through those clouds and see what's really going on. With James Webb, we'll hopefully have a chance to study some of the many planets detected by Kepler and TESS and learn just a little bit more about their atmospheres. In preparation for the launch of James Webb, I led a master's thesis for Charles Sportenbach, who recently defended his thesis at San Francisco State University. And one of the things he developed for his thesis was a framework that he named JET that allows you to put in a list of planets and determine which of those planets would be the best targets for finding a sample of planetary atmospheres over a region of planetary parameter space. We started work on this before Eliza Kempton wrote her transmission spectroscopy metric paper. And that one is definitely well cited and very interesting and quite useful. But if you want another angle looking at this, you can look at Charles's paper and download his JET package to rank targets. Here in this figure, he's showing the planet size versus equilibrium temperature. He's divided it into different categories. So say you wanted to have a comprehensive view of parameter space. His survey then determines which of the targets you would want to look at in order to build up an interesting sample of planets and understand their atmospheres. And we zoom in a little bit. In blue here, he's looking at a bunch of targets from TESS, and those are the best targets that he would suggest for looking at if he wanted to build a whole framework, a whole program of targets with James Webb. And if we zoom in a little more, you can see in gray were all of these simulated TESS planets. In blue were the simulated planets his code selected, and in green are targets that were previously observed. I'm showing you this just so you can get a sense of where the TESS planets fall compared to planets that we previously know about. These are simulated planets instead of real planets, but the main point is still the same, that TESS is filling out the parameter space so that we can really explore the diversity of both planet bulk compositions from the ground using RVs and planet atmospheres from space using James Webb and HST. I'm not going to say too much about the final theme of the TKS survey because this is the one led at Hawaii by Dan Huber and Ashley Chontos, but I wanted to put it up because I know many folks at Cambridge are interested in planets around white dwarfs, and I thought you might enjoy talking to Dan Huber and Ashley about the work they're doing studying planets around stars that are just a little bit younger than the stars you're studying. Okay, so to summarize, what we're doing as a team at Berkeley is to take advantage of the large population of transiting planets detected by Kepler and K2 and TESS in order to really understand the diversity of planet populations and get to know individual planets in more detail. We're looking at the demographics of planetary systems by doing follow-up observations of a large number of candidates. I didn't talk about it today, but we also have a large AO program to study which of these targets are real and which ones are likely to be false positives. We have time at LIC pretty much every semester for AO imaging. So if you have targets where you would like an AO image, please let me know, we can get one for you. We're also probing planetary interior structures, predominantly using Keck-HiRes, but also collaborating with folks around the world to use different spectrographs and team up and combine data sets. We're hoping to determine atmospheric compositions. Hopefully the HST observations will be successful. And we'll be able to say something about the planets in the HIP 41378 system. And then putting everything together in collaboration with the TKS team, we're testing theories of planet formation and evolution. Thank you so much for having me come speak with you today. I'm delighted to answer any questions you might have.
Thanks, Courtney. That was great.